Welcome to the video notes for Section 3E in Chemistry, Empirical and Molecular Formulas. In order to work these notes, you will need a calculator and a periodic table of the elements. A molecular formula is the actual formula of a compound. It tells you what types of elements are in the compound and how many there are of each. For example, the molecular formula for glucose is C6H12O6. And the molecular formula for sodium oxide is Na2O. And the molecular formula for water is H2O. An empirical formula is the simplest whole number ratio of atoms in a compound. For an ionic compound, the molecular formula and the empirical formula are equal. For a molecular compound, you find the empirical formula by reducing. For example, for the molecular compound C3H6, the empirical formula is CH2. Let's try a few others. C6H6 will reduce to CH because both of the 6's can be divided by 6. N2O4 can be reduced to NO2 because you can divide both the 2 and the 4 by 2. C12H10O cannot be reduced. The O has a subscript of 1 and therefore cannot be reduced any further. So in this case, the empirical and molecular formula are the same. However, I really shouldn't have written that 1, sorry. And finally, C8H10N4O2, each of those subscripts can be divided by 2, so you end up with an empirical formula of C4H5N2O. Okay, so what we just did was we found the empirical formula when we already had the molecular formula. But normally what you're going to do is you're going to be finding the empirical formula first. I'm going to walk you through this process, but the two basic steps that you're going to do every time is you're going to convert grams to moles using molar mass, and then you're going to look at each of the numbers of moles and divide them by whichever number is the smallest to get a mole ratio. Okay, here's our first practice problem. We are going to determine the empirical formula when given percentages. Now we need to convert grams to moles, but if we have percentages, what we can do is pretend that we have 100 grams, and if you take any percentage of 100, you're going to get that same number. So 89.5% of 100 is 89.56. So we do that with both numbers. So we're starting with 89.56 grams of barium, and now we're going to convert to moles. We'll also take 10.44 grams of oxygen and change that to moles. Just a reminder on how to convert grams to moles. We're going to use molar mass, which is the bottom number on the periodic table. So as we can see here, the molar mass of barium is 137.328 grams, and that's the number of grams of barium in 1 mole of barium. So we put that down on the bottom so that the grams will cancel out, and then we're going to type it into the calculator. And when you write your answer in this part, you want to make sure that you keep lots of significant digits. So I keep 5 significant digits every time to make my answer later be more accurate. So we got 0.65216 moles of barium. And now we're going to convert oxygen to moles, and we see on the periodic table that the molar mass of oxygen is 15.999 grams per mole. So again, we put the molar mass on the bottom to cancel the grams out, and 1 mole on the top, and then when we type it in, we're going to keep 5 significant digits. So that was our first step, convert grams to moles. And now is a really important step where we're going to look at all of the different numbers of moles and pick which one is smallest, and then divide each of the numbers of moles by the smallest one. So in this case, 0.65216 is smaller, and so we divide both of them by 0.65216. For the top one, we get 1. And for the bottom one, we get 1.00058, which is really, really close to 1. This is our mole ratio. 1 mole of barium to 1 mole of oxygen. So our empirical formula is BaO, 1 mole of each. Another thing you need to know is that sometimes you're going to be given a problem where it doesn't tell you the masses of each element. It tells you the whole compound's mass and then some of the element's masses. And you have to add the masses that you know up and subtract them from the whole to get the mass of the unknown element, like I've done here. Okay, in this problem, we've been given grams, so we don't have to worry about changing from percentages. So what we're going to do is change the grams of carbon, the grams of hydrogen, and the grams of oxygen to moles. I'm going to show that quickly. To convert grams to moles, we look up each molar mass and divide by the molar mass, and then write the answer with 5 significant digits. Okay, now we look at each of our numbers of moles and determine which one's the smallest, which is that bottom one. So we are going to divide each of the numbers of moles by that number and type them into the calculator. The bottom one and the top one here are going to come out to be 1. And when we divide the middle one by the same number, we end up with something that's very close to 3. This gives us a mole ratio of 1 carbon to 3 hydrogens to 1 oxygen, and therefore an empirical formula of CH3O. Unfortunately, the mole ratio does not always come out even right away. If you divide by the smallest number of moles and you get a decimal, then you have to modify your numbers. And the way you do that is by multiplying all of them by a whole number. So, for example, if you get a decimal that is 0.5, 0.5 is 1/2, so you'd have to multiply by 2. If you get 0.333 or 0.667, then that's 1/3 and 2/3, so you'd have to multiply by 3. 0.25 is 1/4 and 0.75 is 3/4, so in that case you'd need to multiply by 4. And then these are less common, but they do sometimes happen. If you get 0.2, 0.4, 0.6, or 0.8, all of those fractions have a 5 on the bottom, and you would need to multiply those by 5. For this example, I'm going to go really quickly through the first 2 steps, which is to convert each number of grams of an element to moles, and then choose which is the smallest number of moles and divide by the smallest. Okay, so when we get our mole ratio, you can see that we got 2 1s, but we also got a 2.67. 0.67 is 2/3, so we have to multiply every number of moles by 3 to get rid of that. 1 times 3 is 3, 2.67 times 3 turns out to be 8, and then 1 times 3 again is 3. So our empirical formula is C3H8O3. Okay, here's the last new thing, and this is going to show you how you will get the molecular formula once you have the empirical formula. You're going to solve for an integer, which we signify as n, and what you're going to do is you're going to take the molecular mass or the molar mass from the problem and divide it by the empirical formula mass. Doing that should get you an integer, and then you will take that integer and multiply it by the empirical formula. I'll show you how. Okay, here's our problem, and as you can see, it gives you a molar mass of this compound. We're going to use that later after we have our empirical formula. First, you're going to solve for your empirical formula. You're going to convert each number of grams to moles and then divide by the smallest number. And as you can see here, we get an empirical formula of CH4N. Now we're going to use that formula that I just showed you, where you take the molar mass of the compound divided by the empirical formula mass. So the molar mass is 60.10 as given in the problem, and then the empirical formula mass you are going to add up from the periodic table. So we add 1 carbon plus 4 hydrogens plus 1 nitrogen to get the empirical formula mass. When we divide 60.10 by 30.05, we get the integer 2. So 2 is our n, and then what we're going to do with that is we're going to take it times the subscripts on each of the elements in our empirical formula. So we take 2 times CH4N, and we end up with C2H8N2. That is our molecular formula.